Welcome to Ask and Learn.
In this problem, we have a block that weighs 5 pounds and travels at 10 feet per second that strikes a platform that has a spring underneath. And we want to find the distance that this spring compresses after the collision with the block. Now, its weight of 5 pounds we can convert to mass by dividing by 32.2 feet per second squared. And we're also given the stiffness of the spring, which is K is equal to 400 pounds per feet. Now, because we're dealing with the velocity, this block has kinetic energy, and it also has a weight, so there's a force being produced as it travels before it strikes the spring. And the spring itself has a force, so it will produce a work in the opposite direction of this block when it collides. So because we're dealing with work and we're dealing with energy, we can use the work energy principle, which is the initial kinetic energy plus the work being done by the forces is equal to the final kinetic energy. But because the block stops moving after the collision, its final kinetic energy will be zero because the velocity will be zero. So we're left with the initial kinetic energy, 1/2 times the mass times the velocity, we'll call V1 squared, plus the work being done by the forces equals 0. We'll call this equation 1. So now let's look at the work being done by the forces. So the forces involved are the weight due to the block and the force due to the spring. So let's look first at the block. So work is force times distance. So we have the weight of this block times the distance. So we know it travels 3 feet, which we'll call SA, plus the distance this spring compresses after the collision. Okay, that's for the block. Now let's look at the spring. And again, the spring will create a work in the opposite direction of this block. So work will be negative here. And the force due to the spring is 1/2 K times S, we'll call it S final squared, minus 1/2 K S initial squared. And all this is in parentheses. So now let's look at first S initial. Well, the platform pushes down the spring to a distance of 1 foot, but uncompressed, the length of the spring is actually 1.75 feet. So initially, the distance of the spring is that 1.75, the uncompressed length, minus 1 foot, the distance is compressed to. So SI will be 0.75 feet. We'll call this S1, which means that S final, the final distance that the spring compresses, will be that 0.75 feet plus some distance it'll compress after the collision, which is S2. So now let's plug this back in to our equation for work and plug in some of the values we know. So we have the weight of this block, which is 5 times parentheses SA is 3 feet, the distance the block travels, plus S2 minus 1/2 K is 400. And we're factoring out the 1/2 K since both have it. So now we have in parentheses, in brackets, we have S final, which is 0.75 plus S2 squared minus S1 squared. And again, remember S1 is 0.75 feet. So now let's distribute the 5, factor this, and also distribute the 1/2 times 400, which is just 200. So let's try to clean this up. So we have 15 plus 5 S2 minus, so we distribute the 200, so we have 200 times S2 squared minus 300 S2 minus 112 plus 112.5. So combining terms, we have minus 200 S2 squared minus 295 S2 plus 15.5. So now we can plug this in to our one equation. So we have the initial kinetic energy, 1/2 times the mass, 0.155 times 10 squared minus 200 S2 squared minus 295 S2 plus 15.5. So again, and this is all equal to 0. So combined like terms again. And then multiply by a -1 just to make this negative 200 positive. So we have 200 S2 squared plus 295 S2 minus 23.25 equals 0. So to solve for S2, we need to use the quadratic equation. So S2 will equal minus 295 plus or minus square root, and then inside the square root is 295 squared minus 4 times 200 times minus 23.25. And again, all of this square root, and everything is divided by 2 times 200. So when we plug this into the calculator, we get S2 is equal to 0.075 feet.